Somewhere in the freezing, silent expanse of deep space, a massive object is moving. It has no star to orbit and emits no light, drifting blindly through the dark on a path straight toward us. These rogue planets are common features of the galaxy. During the chaotic early years when solar systems form, massive gravitational shifts routinely sling smaller planets completely out into the void. Current estimates suggest billions of them wander the Milky Way alone. The difficulty lies in our inability to see them coming. Because they lack a parent star to illuminate them, they reflect almost zero light. To standard optical telescopes, they remain practically invisible. To find them, astronomers rely on infrared technology to hunt for faint heat signatures against the absolute cold of space. This image shows the scale of that challenge. Among thousands of bright stars, those tiny circled blips are the thermal signatures we're looking for. Our solar system operates as a precisely balanced gravitational machine, where every planet and moon sits in an orbit maintained by the sun's massive pull. A massive, unexpected gravitational force entering our system triggers a cataclysmic chain reaction of orbital chaos, far more destructive than any single physical impact. The disruption begins quietly. The rogue planet makes its first undetected entry into the frigid outer reaches of our solar system, crossing regions like the Kuiper Belt, far beyond the icy isolation of Pluto. Out here, billions of dormant comets and icy chunks of debris drift slowly in the dark. The rogue planet acts like a cosmic bowling ball plowing directly through these outer fields. The sheer mass of the wandering planet physically alters the trajectory of thousands of long-period comets. It sweeps up this massive field of rock and ice and flings it violently inward, straight toward the sun. This incoming wave of debris creates conditions similar to the late heavy bombardment, a period roughly 4 billion years ago when the surface of early Earth was relentlessly pounded by cosmic shrapnel. Even if the rogue planet itself never makes it past the gas giants, our inner solar system is already compromised. Earth is destined to face a severe firestorm of asteroid and comet impacts, triggering mass extinctions from the falling debris alone. But the wanderer continues inward, crossing the orbital paths of the gas giants and entering Jupiter's domain. Jupiter's massive gravity is crucial to keeping the surrounding planets stable. When the rogue planet disrupts Jupiter's orbit even slightly, that instability amplifies outward. This resonance effect immediately throws the nearby asteroid belt into complete chaos, sending an entirely new wave of rocks toward Earth. Eventually, the rogue planet crosses into the inner solar system. As it approaches Earth, its gravitational pull begins to compete directly with our own moon. The immediate effects on our surface are catastrophic. The shifting gravitational forces pull violently at our oceans, creating mega tsunamis hundreds of meters high that sweep inland and submerge coastal cities within hours. This gravitational pull stretches and compresses Earth's rocky crust with extreme uneven stress. We see the consequences of this tidal friction on Jupiter's moon Io, where a constant gravitational tug-of-war fuels violent, unending volcanic eruptions. On Earth, this geological stress translates to massive global earthquakes, erupting fault lines, and superstorms. Long before the rogue planet physically touches us, its mere proximity cracks the surface and leaves it completely uninhabitable. Then comes the final critical stage of the event. Astrophysics models point to two distinct terminal outcomes for this close encounter. The first is a near flyby. Even if the massive planet entirely misses Earth, its passing gravity can pull our planet's orbit. This chart shows what happens if Earth's path shifts slightly outward by just 1 or 2%. That tiny shift in our distance from the sun dictates our survival. If we are pulled further away, our oceans permanently freeze over into solid ice. If we are pushed closer, they boil away into the atmosphere. The second scenario is a direct physical impact. If the wandering planet collides with Earth, the crust vaporizes instantly upon contact. The kinetic energy released in this split second equals roughly 100 million times the global nuclear arsenal. It strips away our entire atmosphere and evaporates whatever is left of the oceans, mirroring the ancient planetary collision that formed our moon billions of years ago. The climax of this terrifying event guarantees the complete physical destruction or permanent cosmic displacement of our world entirely. There is one final question to ask. What happens if Earth somehow survives the physical encounter, but is ripped away from the sun's gravitational grasp? As the immense rogue planet moves on, its gravity could drag Earth along with it, ejecting us straight out of the solar system. Our home would become a dark, frozen rogue planet itself. Without the sun's warmth, the surface ecosystem collapses completely within days. The only surviving life forms would be isolated near deep-sea hydrothermal vents, feeding off the faint radioactive heat of Earth's decaying core. Planetary ejection, orbital disruption, and world-shattering collisions are confirmed mechanisms of our universe. We see the evidence of them everywhere we look. While humanity scans the skies for visible asteroids and predictable orbits, the ultimate inescapable threat might not be something we can see. It is a silent, wandering giant drifting through the dark, waiting to cross our path.